So this is a lecture for March 25th, 2020. The topic for this lecture is the change of variable in double integration. In the previous lecture on March 23rd, I talked about how to compute double integration by figuring out the lower bounds and upper bounds for inner integration and external integration. Now, why do we do a change of variable in double integration? The main reason is, in certain cases, especially the region we compute the double integration over can include a circle-like patterns, like I mentioned over here, showed over here. So we have a circle-like, or like this is a 3/4 of a circle. For this case, although we can still use the method mentioned before to compute a double integration, but it turns out that the way to change the method to change the variable used in the double integration can dramatically decrease the computational complexity. Okay, and in some cases this change can be very efficient. So that's the reason we started the method called change of variable in double integration. Okay, to give you an example, I want to show you why we do double integration and how we double integration. Use this very simple example. So assuming we have a region given by S, so this area is a 2D space and is a 3/4 of a circle. The circle is centered as an origin with radius 1. Now the area S is composed of first quadrant, second quadrant, not the third quadrant but last quadrant, fourth quadrant. They want to integrate over a function of 1. Okay, this is a very simple one, over dx dy. Also, as I mentioned in the previous lecture, this is just the area of this S, because you can calculate this is just 3 or 4, 3/4 times the area. The total area is pi times 1 squared. You can calculate this one. Okay, the purpose is not trying to figure the number, you can figure it out by the meaning. In the next example I show you, you won't be able to have this result, but you can still use the change of variable to make the computation very efficient. Okay, what I mean by this is, if you do this one, if you would use the previous method I mentioned for the double integration, this can be written as inner integration given by this, the blue box, and also you have an outside one, which is the red one. It's external integration. Now the challenge for the external integration is, for the external one, okay, as I mentioned before, for the y's outside one a variable, the lower bound, upper bound is always try to figure out the smallest y and the largest y you have for this area. So for this area, the smallest y is here, right? This is y equal to -1, and this is positive one is the largest one. You cannot go beyond that because this is a circle like shape. So you can see this is -1 to 1. Now the key problem comes from here. When you do the lower bound, upper bound for x, it's kind of hard, because for different, as mentioned, for different y, this one should consider different y. So let's say if my y is starting from here, this is my y. Okay, let's put it right kind of. If y is over here, now as mentioned before, is you let y to be a constant, okay, which means your y is always this value. You put a straight line over here, okay, and you cut across this area S. You find out what is the lowest and what is the lower bound, what is the upper bound. So this value and this value will determine the lower bound, upper bound. Now, it's interesting if you take different y's over here, so you could have different ones, right? Now, if you put over here, y over here, kind of that's a little bit weird, because this one you start always from 0, right? For if your y starts below than 0, you always start from here to here, right? From 0 to a certain number. However, if your y is above 0, you can start from not 0, from some value. So essentially it becomes harder to figure out what's the lower bound. The lower bound has two components. One is positive, you have this. One is negative, you do this, right? But the upper bound is always given by this. Okay, this is your upper bound. Okay, so the problem is this becomes a little bit complex, and you cannot formulate this one as a unique one, because you could have two different cases. Although one method you can do is, well, I can rewrite this one this way. Okay, let's rewrite. You can do, well, this one equal to integration of S1. So S1 I mean by this is this component. This is my S1. So this is my S1. It's just above when y is not negative. And S2 is this. So you can have S2. This S2 area is below that. So S2, S1 basically is the first quadrant, the second quadrant, and the S2 is just the fourth quadrant. You can do this one. Yes, it is equal to, the original integration is equal to 1 time dx dy over the area S1 plus S2 1 over dx dy, which is true. Now you can figure lower bound. You can find lower bound, upper bound for this one. 1 dx lower bound, upper bound dy. Yeah, true. So for this case, you can figure lower bound, upper bound, and lower bound, upper bound, lower bound, upper bound. 1 time dx dy. You can do that for each one. For this one, you can figure lower bound, upper bound, lower bound, upper bound by using the method I mentioned on March 23rd, which is fine. But the computation becomes more complex. Okay. So what is the easy way we can do this? Okay. Now easy way, assuming I don't use the physical meaning of that because one's so special, right? So you can do the physical meaning. Yeah. Assuming we still use the calculation doing the double integrations. Now one method you can do is, well, you naturally think about it. If I change a variable, okay, I want to integrate, not use xy because that's a problem, right? If I could, because this is a circle like a shape, now this area can be represented as any point xy by letting x equal to r cosine theta and y equal to r sine theta. So the entire area, it's very hard to specify lower bound, upper bound, and over, especially for x, right? But if I do the change of variable, if I want to represent this entire area of S, what it only needs is to let r be within 0 and 1, and theta be within negative pi over 2 to essentially pi. Okay. The reason is if I let r to be, let's say if r to be 1, if r is 1, so the radius is 1, so you swipe from negative pi over 2 to pi. So you basically talk about this line, this circle, the boundaries over here. So once you mix this r to be smaller, because it's 0 from 1, you make it smaller, you're gonna swap another one. It's gonna another circle, it's getting smaller. So you can keep on doing. You will cover the entire area. So this is a good representation because this is simpler than x and y. So you will cover everything basically. So this representation will cover, as you let r go to 0, you'll stay this point. So this will cover entire S area, which is true. Yeah, if I do this variable, which is true. Now the problem becomes, if I do this one, now originally my problem is I want to integrate this one over dx dy. This is my area. This is if you consider dx dy, it's sort of the very tiny square over here. Right over here is tiny square dx dy. Okay, integrate there. Well, the problem is, if I do this way, I cannot write this into di something s into integrate over s times dr d theta because I want to integrate over dr d theta. Dx dy is so difficult to represent this area because I want to find some x, something over here, something here, and y, something over here, something over here to represent s. As I know here, this is easy to use r and theta because r just less than 0 to 1, theta 9 over 2 to pi. Now the problem is not, you cannot put just 1 over here. The reason is dx times dy is not a dr d theta. So dx dy is the length, right? R is still length, but theta is the angle. This is different, right? So that's not the same. So what's the relationship between these two? So that's the problem, right? I figured out the reason because if I replace dx dy by dr d theta directly, this won't happen. This is not equal. So I have to figure out a way to do it. Okay, how do I do it? Okay, fortunately we have the existing tools that can calculate a relationship between dx dy and dr d theta. which is given by called Jacobian. This is called Jacobian. Okay, Jacobian is sort of determined by, this is how we determine by the Jacobian. Jacobian is given by partial x over partial r, partial x over partial theta, partial r over partial y, partial I over r, or partial y over theta. Basically what it means is we have two variables over here, x and y, and also on the right hand side, x and y can be represented as a function of two new variables, r and theta. So you can sort of consider this is, oh, I have function x as f, r and theta, y is g, r and theta, because these two functions are different. One is cosine, one different. So what happens is you're trying to figure out, okay, partial x over one variable. This is, you consider here, partial x over each individual variable, because x is represented by r and theta. You have partial x over partial r, and then you have partial x over partial theta. And this is for y. You do partial y over partial r and partial y over partial theta. Okay, you can swap the order, doesn't matter. You can swap the order. You can do partial x over partial theta first, then partial x over partial r. That's the same. Okay, it doesn't really matter. Okay, so what the Jacobian says, and this is also well started tool, says dx dy is equal to Jacobian. So this is called determinant. It's a determinant of that. Jacobian time dr d theta. Okay, which means if I go back to the previous one, this guy is equal to, not equal to 1 of course, but is equal to this guy time Jacobian. Okay, Jacobian is a computer over here. It's given by the determinant of partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. Okay, so we can calculate, since we already have this relationship, this f, this function of x in terms of r and theta, the function y in terms of r theta, we can calculate this partial derivatives. So because x is r times cosine theta, so the partial x partial r is just cosine theta, and you similarly you compute all these numbers here. Okay, so the determinant, this guy, the determinant of this 2 by 2 matrix is just cosine theta times r cosine theta minus the off diagonal, the product of off diagonal entries, which is sine theta time minus r sine theta. Because you minus that, so this may become plus. So it's r cosine theta squared plus r sine theta squared, which is r times cosine theta squared plus r sine theta squared, which is r. Okay, so if you do that way, now you can calculate this this result. Okay, which is, if I do that one, so this is again the original S area. So this one is given by integration, like I mentioned over here. You had to put a j, so this is a relation. So you can put a j over here. You put a Jacobian over here. The Jacobian here is just r, right? So this guy, so the original integration over here, the double integration I mentioned over here is just given by integration of 1 time Jacobian. Don't forget about this one. Don't put r time dr d theta. So which is also r dr d theta, because Jacobian is already calculated by r. Now we can use the double integration, the method I mentioned before. So the same procedure applies. Is you have inner integration over here, you have outer integration over here. So now for the outer integration, we just figure out what is the angle. So remember the angle here is this angle is, this is your theta. Okay. Now theta, what is the maximum of theta? So to cover a region, what is the smallest and largest? The smallest one to go from here, right? It's right here. You have negative pi over 2, and you go all the way to pi. Okay, so this the integration is from negative pi over 2. This is pi, and the r is for each theta. It doesn't matter which theta you are in. This one should be true for any theta, right? If I for any theta I select theta, yeah, your radius will go from 0 to 1. It doesn't matter where you are. It's always from 0 to 1. So this is from 0 to 1. So now we can do the integration, which is, let's calculate the double integration, which is, and it keeps the outside to be unchanged. Let's do the integration for the inside. So integration of r over r is 1/2 r squared 0 to 1 d theta, which is this is 1/2 r squared. 1/2 r squared times 1/2 1 squared is 1/2 minus 1/2 times z squared is 1/2. So this is 1/2 negative pi over 2 pi. This is 1/2 d theta. So this will be just 1/2 theta, and pi negative pi over 2, so it's a 1/2 pi minus 2 pi is plus pi over 2, so this is 3 pi over 4, right? If you go back to the previous one, we do have 3 pi over 4, so that's the same, okay, which means the same. So now let's take a look at the second example. Okay, for this example, it's a little bit complex. The area is still the same, as I already mentioned before. The difference here is I don't integrate over 1, but I integrate over x. Okay, now you cannot use the previous method of physical mean anymore, right? Because I'm integrating over x. But you still can use the method I mentioned before. So what I do is this one again. I can write this one into s over x. X is what? If I remember, what is x? If I want to change a variable, right? I want to write x in this form. X is r times cosine theta. Basically, I want to write here is dr d theta. So you should change every x and y to be r and theta. You cannot have x over here. So x is r cosine theta. Y is r sine theta. So I have x, change x to cosine theta, r cosine theta. Okay, and don't forget that you cannot do this directly. You have to time Jacobian, right? The Jacobian is calculated as r over here. So let's put the r at the front. So this is r over here. So this is just r squared. Okay, so we have this one. Okay, so this one, according to what I mentioned before, this is a still integration, double integration, r squared cosine theta dr d theta. So the lower bound and upper bound will be the same because the same region will be the same. So it will be just r will be from 0 to 1, and this is from negative pi over 2 to pi. Okay, so this is the same way because the region area is the same as previous, so the lower bound and upper bound will be the same. Okay, integration from pi negative pi over 2, and this d theta is not changed. Let's compute the inside. Now remember, for this one we consider theta to be a constant. So actually I can move it out. I can just move the cosine theta here. So you can move it outside. So the integration of pi r squared is just 1/3 of r cubed from 0 to 1. Okay, so this one gives us pi negative pi over 2 cosine theta. We still keep it here, so this is 1/3 times r cubed. Okay, 1 cube is 1 minus 1/3 times 0 to the cube is 0, so it's 1/3 d theta. So integration over here is, so I keep it the 1/3 outside, 1/3. So integration of cosine theta is sine theta over pi and negative pi over 2. Okay, so which is 1/3 sine pi minus 1/3 sine negative pi over 2. So sine pi is 0, gone, and this sine pi negative pi over 2, this is negative 1, so it's basically 1/3. Okay, so this is the second one. So you can see this is computation is fairly easy. If you do the dx dy, you have to divide into 2 different cases. For each case you can compute all the integration. It can be much more complex. Okay, now let me summarize in general how you do it. For the change of variable, how you would do it. Okay, so the change of variable, assuming this is a general case. Okay, so assuming I have integration over s of f x and y dx dy. So I want this one, assuming I have x is f unit v and my y is g unit v. Okay, now this one integration is given by integration of s f. You replace the x by no, let me rewrite this one as is, okay, is m, and so I don't want to use the same f, m unit v n and unit v. You basically replace all your x by unit v because I don't want to have it. This one you become du and dv over here. Now this one, okay, du and dv. Now this one you have a Jacobian. Jacobian is given by partial m over partial u partial m over partial v, and partial n over partial u, partial n over partial v. And this is computed determinate as 2 by 2 matrix. So this is a general form. This is a general form you use for any sort of change of variable, because this is a special case of a change of variable you use. We use an example. You can also do a change of variable for any other case when you write x as a function of u and v and y as a function of u and v. So the key problem you have to remember is you must write x and y as the same variable u and v. Okay, the same u and v. Then you do the partial derivative. That makes sense. Okay, so that's the general. That's the main idea about the change of variable in double integration.